Go to Chapter 4, Volumes of Revolution. You might remember there's a chapter on volumes of revolution in the Core Pure 1 book. When you return to it in Core Pure 2, there's very little additional theory we need to cover. It's just that the integrals and the processes will feel a bit more involved because by the time we get to Core Pure 2, the specification in the book doesn't have to assume that you might not have covered Year 13 A-level maths content by this point. Which means, for our first example question, we can expect things like double angle identities to be relevant and required. Now, the one additional thing that's in this chapter that isn't in the comparable chapter in Core Pure 1 is parametric curves. And there are ways of dealing with volumes of revolution explicitly within parametric form, but it's also often possible to convert into a Cartesian form. And although that's not always the most efficient way to solve a problem, if it is possible, as you can see in this question, sometimes that's the route that you're guided into. So I'd encourage you to pause and have a play with this, see how much you can already remember about volumes of revolution, see if you can recreate the formulas, have a careful look at the diagram, use your knowledge of things like polar coordinates to remind you how important it is to figure out where you are on the curve at different points, and see how far you get through the question. In a moment, I'm going to continue and I'll talk through my example. Let's begin with part A. This is a show that question. They're asking us to convert the parametric equations that we're given into this specific Cartesian form. Even if you can't manage this section, you could still make use of this Cartesian equation in order to solve the next part of the question. But given what we've been told, it should be possible to find a way to convert those trigonometric parametric equations into something that only involves x squared, y to the 4, y cubed. What I wouldn't recommend you try to do here is automatically jump straight to let me work out the left-hand side and the right-hand side and then show that they're the same. Because although that should work, in this case it would involve expanding 1 plus sine theta to the power of 4 and to the power of 3. And even if you're quick with your binomial, that's quite tedious. You'll end up with lots of sine squared, sine cubed, sine to the power of 4s, and so on, that you don't necessarily want kicking around to try to tidy up. So there might well be a better way. And the better way is actually the method you would use if you weren't given the Cartesian equation in the first place. If they just said find a Cartesian equation, what would you do first? Well, you'd look for a connection between the expressions for x and the expression for y. It's not necessarily always going to be possible or even recommended to try to make theta or t the subject. But if you've got trig involved, we should start looking for a way to connect or relate the trigonometric functions. That's going to be a non-starter unless we can get rid of the sine 2 theta. So the very first thing I'm going to do is tidy up the sine 2 theta using my double angle identity. Sine 2 theta equals 2 sine theta cos theta. Hopefully you spot that very quickly, and then you recognize, oh, I could take out a factor of cos theta. And as soon as you do that, 1 plus sine theta should jump out at you. That is almost identical to the expression for y. Throw in a minus sign, and we've got x equal to cos theta multiplied by minus y. Now, if we look at what we were asked to find, it's got an x squared in it rather than an x. Also, anytime you're trying to find connections between trig functions when you're dealing with parametrics, it's almost always going to come down at some point to making use of the Pythagorean identity that connects sine squared theta and cos squared theta. So it makes sense at this point to square both sides of what I've ended up with. X equals minus y cos theta, so x squared equals y squared cos squared theta. Notice that your minus sign will disappear because you're squaring things. We've got to pay attention to that. If we end up with something that's almost but not quite the answer we were asked for, we can go back, find and fix our mistakes. That's what I did the first time I went through this. Made all sorts of silly sign errors, but I was able to recognize that I had and go back and fix them. Now, the reason this is helpful is that I can already see an easy way to rearrange the y equals negative 1 plus sine theta expression so that I can get sine theta in terms of y. And if I can do that, and I also have an equation where I'm trying to get rid of cos squared theta, swap it out for something involving y or x or something, I can use the fact that sine squared theta add cos squared theta equals 1. So I'm going to rearrange to get sine theta in terms of y, and that just gives me minus y minus 1. And then because sine squared theta is going to be minus y minus 1 squared, I can subtract that from 1 and get cos squared theta. I know it looks a bit messy, there's a lot of negatives in there, but remember, if you're squaring something, then the sign of the thing you're squaring becomes irrelevant. So if I was squaring y plus 1, it would give me exactly the same result as if I'm squaring minus y minus 1. If you like, you can think of it as taking out a factor of minus 1 from the entire bracket, but the process of doing that means squaring the minus 1. So it's not actually that messy to expand. Hopefully you won't get too confused. And when we subtract all of that from 1, we end up with a minus y squared, a minus 2y, and then the 1 take away 1 disappears. At that point, I can sub it back into the expression I had above, x squared equals y squared times cos squared theta. And the cos squared theta gets replaced with this, and I'm almost home free. The last little step is to put the y squared into the bracket and take the minus sign out of the bracket so that it perfectly matches what we've been asked to show. For this second part of the question, we're asked to find the volume of the pendulum. So this will be the classic volume of revolution formula. Pi x squared dy is just one of the two options. This is the version we use when x represents the radius, and then the small change in y is going to be the very, very tiny height of all the little cylinders. And in this case, because we're going to be rotating around the y-axis, we need this version. If we were rotating around the x-axis, we'd want pi y squared dx. Now, the next thing to notice is that because this integral is an integral in terms of y, it's with respect to y, and we're going to replace x squared with something involving y in a second, the limits are also y values. And you could be forgiven for thinking that y is equal to 0 at the bottom and 2 at the top. That's what the 2 centimeter height seems to suggest. But we have to be very careful with that. We've not been given a set of axes. We can't go making assumptions without double checking them. So let's take a look once more at the original equations that produce this model. And let's see what happens at different values of theta. If we want to know in particular what the y value would be at the very bottom or the very top, that's probably going to be the most efficient way to figure out what the limits should be, because I want to know the y coordinates of the lowest point and the highest point. So let's just focus on y. The negative of 1 plus sine theta. Well, that's going to vary between the value we get when sine theta is 1 and the value we get when sine theta is minus 1. Theta goes from 0 to 2 pi, so we get the full range of sine values all the way from 0 up to 1, down to 0, down to minus 1, and back up to 0. So if sine theta is going between 1 and minus 1, 1 plus sine theta goes between 2 and 0. Put a minus in front, we get between minus 2 and 0, which means the y values in question here are actually minus 2 and 0. This teardrop shape that we've ended up with, turns out it begins when y is, or whether it begins or not, the top is when y equals 0, and the bottom is when y equals minus 2. We could look at what the x coordinate is at those points as well, or work out what theta would be, but the simplest thing for this is we care about the y coordinates, that's all. As long as we integrate between the appropriate y values, this should work fine. The next bit is just substituting in values. So we'll put the expression for x squared that we calculated in the previous part of the question in place of x, or in place of x squared rather. It's already been squared, so there's no need to multiply this by itself or anything like that. And now we just integrate, and don't forget to multiply by the pi. I've taken the factor of negative 1 out of the entire bracket, but notice the limits go from minus 2 to 0. If you plug in incorrect limits into this, you're going to end up getting a weird answer. You might end up with something that just gives you the negative of what it should, and you can't just change the sign at the end and hope everything's fine. You've got to go back and make sure your limits match. So when I do this properly, I'll get a negative inside the bracket, but I've also got a negative outside the bracket. And it tidies itself up and gives me 8 pi by 5. And I've also calculated the approximate volume, which is going to be helpful for sense checking my answer. Does it look like the kind of thing that might plausibly have a volume of 5.03 cubic centimeters? That's what you'd be looking for to verify that final value. So as a quick recap, if we need to do an integral involving parametrics, this is what you would have learned in A-level maths. If you've got the integral of y with respect to x between limits for x, you can convert it into a parametric integral, but we have to make sure it's an integral with respect to t, which means we need to write dt on the end. And that's allowed provided we also put a dt on the bottom. So we're effectively multiplying by dt by dt, which is equivalent to multiplying by 1. It's a little weirder than a regular fraction because it's made from infinitesimals, but it still works in this case. Effectively, it's like applying chain rule. And the beauty of this is that if y is a function of t and x is a function of t, well, we could differentiate the x one to get dx by dt, and then both y and dx by dt would be functions of t. We can put them into this integral, integrate them with respect to t. The one crucial detail that you need to not forget is that you also have to change the limits if you're going to do this integral, because everything needs to be in terms of t. Now, we can adapt this process very simply for volumes of revolution. All that really changes is how we complete the integral. So if y is written in terms of t and x is given in terms of t, then we've already got y squared in terms of t. We can differentiate the x with respect to t and get an expression in terms of t for that bit. As long as we can convert our limits, then we end up with an integral that involves dt rather than one that involves dx. And of course, although I've not written it out, this would work just as well if you had pi x squared dy. You just need to do dy by dt times dt at the end of your integral. So the process is the same. All you have to do is make sure you include that dt and change your limits. You can try a question now. This one's been set up so that it involves trig functions. There will be some double angles involved as well. Let's see how well we get on with that. We're trying to create a thimble shape, so there's sort of flattened shape at the bottom and then curves upwards. Pay close attention to the values of t so you can work out what your limits should be. But chances are we're going to go from 0 to pi by 2. You'll want to double check which way around your limits might need to be and when you reach each of those points. Notice that we're rotating around the y-axis. Give this question a try. If you wait a couple of seconds, I'm going to put up some hints to help you scaffold your answer if you're a little bit stuck or you want some pointers without getting all the solutions. So these are the steps that I'd recommend you follow. If you're a little stuck at a certain point, follow these. Annotate the diagram by thinking about your t values. Look at what happens at 0 and at pi by 2 and indicate where those points occur. Set up your integral. Think about whether it's a pi x squared dy or a pi y squared dx situation. Adapt using dt and change your limits to t values. And finally, have a go at evaluating the integral. You might find when you've simplified it, a substitution is going to work quite nicely, or possibly inspection. So we begin by annotating the diagram. When you replace t with 0 in the x and y equations, you should find you get 1, 1. X is 1 and y is 1. And if we sub in t equals pi by 2, we're going to get 0 for x and minus 1 for y. So straight away I can see that the bottom of my shape happens when t is pi by 2 and the top is when t is 0, which might seem a little bit backwards. That's why it's important to check the limits, even if you're confident that the 0 to pi by 2 range does correspond to the entire curve. You need to know exactly where. In some cases, the curve might be traced out twice, and all sorts of other weird things can happen. So when I set up my integral, I'm also choosing the pi x squared dy version because the y-axis is the axis of rotation, making x the radius at any given point. So pi r squared becomes pi x squared. And then because I'm integrating from minus 1 to 1, they're the y values, I need to be integrating t values between pi by 2 at the bottom end and 0 at the top end. It may feel backwards, but this is the order that the t values correspond to the appropriate y values. So this is what's going to give me a sensible result. The only other change I've made is to put dt at the end and a dt underneath the dy to cancel out. That way, when I get to the next step, I can replace x squared with root cos t squared, and I can replace dy by dt with the derivative of cos 2t with respect to t. So I'll do that. I've done a little more simplifying by tidying up that double angle. If I want to integrate something with trig that has some double angles and some not, and all multiplied together, it's going to make it more straightforward if I can write it in the format that I've got there on the right, cos squared t times sine t. So replace sine 2t with 2 sine t cos t. I've pulled out the factor of minus 4 that I end up with, and now I can concentrate on the rest of the integral. You might be thinking, I've got a minus sign, and I've got limits that are a funny way round. Why don't I get rid of the minus sign and swap the limits? That's perfectly valid. If you're happy doing that, by all means do that. If you swap the limits of an integral, the only effect is that it will give you the exact negative of what you would have got, because it changes which order you subtract things at the end. So if you're happy with that, feel free. I'm going to leave it as it is so that we don't confuse people unnecessarily. But the next step, hopefully, is where you recognize either that there is a suitable substitution, or if you're feeling particularly confident, you apply integration by inspection. You notice the format matches what you would expect if you were differentiating cos cubed t. Because chain rule tells you to differentiate cos cubed t, you turn it into 3 lots of cos squared t, but then you multiply by the derivative of cos t, which is negative sine t. If you reverse engineer that, the minus 3 that would come out if you differentiate cos cubed t can be incorporated as minus a third in the original integral, so that when I integrate cos squared t times sine t, I just get minus a third cos cubed t. As I say, if that feels like too much of a jump to do, to sort of reverse chain rule inspection, then do it with a substitution. Use the fact that the derivative of cos t appears within your integral, because the derivative of cos t is minus sine t, and then you'll just end up with u squared in your integral with respect to u, and things get much nicer and simpler. U squared becomes u cubed over 3, and that's where the 1/3 comes from. The minus comes from the fact that you'll have pulled out another minus sign, probably tidied it up a little bit more than mine as well. The last thing is to sub in your limits, and you end up with an answer. And if you can, check that your answer makes sense. When I first did this question, I think my answer was off by a factor of 2, because I forgot that sine 2t gives me 2 lots of sine t cos t, or something daft like that. But when I look back at the graph, I can see that a nice way to estimate it will be to imagine a cylinder of radius 1 and height 2. So that would give me a volume of 2 lots of pi. But then, because I've got something that's quite a bit smaller than that, I'm expecting an answer smaller than 2 pi. It's not quite as low as pi, but it should be probably somewhere between pi and 2 pi. So that seems to fit what I've got. So now I'm happy with the answer I've finally ended up with. The next thing for you guys to try is this question from exercise 4C. There's plenty of other useful practice questions in 4C as well. This one's quite nice because, number one, it breaks things down for you into a few steps, and number two, it illustrates for you how you should get exactly the same result if you're able to convert your equations into a Cartesian form as if you just use the parametric form. I will go through solutions for this as well if you like, but first you've got to pause and give this one a try and come back to the video when you've had a go at solving the problem for yourselves. So, assuming you were done with that question, let's talk through how I would solve it. Write down the values of t corresponding to x equals e squared and x equals e cubed. It's a write down question. It's not going to require a huge amount of working out. E to the power t is what x is equal to. So if x is e squared and x is e to the t, then t must be 2. And the same thing happens with e to the 3. So we've kind of chosen values that give nice t values, which is going to help a little bit. When we reach the next step, we always set up the volume of revolution integral in the standard format with y squared dx or x squared dy, depending on what we're rotating around. In this case, did you notice we're rotating around the x-axis? So that makes the y coordinate the radius, and pi r squared h becomes pi y squared delta x, and then the infinite sum, the integral, will become pi y squared dx. The limits are obviously limits for x when it's in its original format, but when I modify it so it works for t, the limits need to be changed to t values, and I replace dx with dx by dt, dt. And then it's just substituting in. So the y squared bit is quite nice. Dx by dt is the derivative of e to the t, but that's still just e to the t. And then it comes down to whether you remember how to integrate expressions like this. Now there's a couple of ways you can break this apart if you want to initially. You could write it as t e to the t, take away e to the t, and say, well, at least I can integrate e to the t, so I'll focus on t e to the t. And maybe it'll be easier to spot what's happening when you do that. But it's not strictly necessary. If you want to keep it as t minus 1 multiplied by e to the t, you can do that as well. But this should jump out at most of us as an integration by parts question. Substitution is not going to help because a linear expression and an exponential expression have very little in common with each other. So we're not going to find the derivative of one bit appearing inside another bit or anything like that. So since it's two things multiplied and parts would seem like a promising approach, we're going to try that. A good way to check, to sort of look ahead into the future of a method like parts is just to ask yourself, would it be beneficial if I could replace the product of these two functions with the product of the derivative of one of them and the integral of the other one? So in a sense, you're making one of the two terms in the product more complicated, but the trade-off allows you to make the other one less complicated. And the beauty of it for something like this is that e to the t doesn't really get more or less complicated when you integrate or differentiate. So I can do what I like with that one. But t minus 1 will get much nicer if I can differentiate it. It'll reduce to a constant, and I can deal with the integral of a constant times e to the t. So it's going to be the perfect method for this. Take care with your notation. What I've done here is I've set up an indefinite integral, so I'm not worrying about limits yet, just so I can evaluate and tidy up what do I get if I integrate t minus 1 e to the t. So I apply the parts formula, I get a result, and once I've got that result, I'm practically there. I could complete that bit and do the integral of e to the t, it's just e to the t, and then put it together with the rest, and then I can go back to my volume question and substitute those things in. So t minus 1 e to the t, take away the integral of e to the t is just e to the t. So I end up with t minus 2 e to the t, and then I need to put my limits in. The limits of 2 and 3, that all simplifies down quite nicely to pi e cubed. For the next part of this question, part C, they're switching tack a little bit. We've already found the volume of the solid of revolution. For part C, we're going to find the Cartesian equation of the curve. And the simplest way to do that, especially if you're paying attention to the format they've given you, is, well, let's try squaring y. With something like this, it all comes down to making t the subject so that you can eliminate t. So if we square y, then we find that y squared is t minus 1. And if we use the natural log on x equals e to the t, we find that t is ln x. And therefore, we can just replace t with ln x, and out pops y squared equals ln x minus 1. For the next bit, I've actually called this integral v because I know that it should also correspond to the volume of revolution. It's pi times the integral from one x value to another x value of y squared with respect to x. So it should, in theory, give me exactly the same result that I got before. But we can work through it and find out. The first thing you'll notice is that this is also a parts integral, if you're aware of this sort of sneakiness. What I've done here is I've said, well, I can integrate minus 1. I'll worry about that later. Let me focus on ln x. A very common mistake here is to think, oh, ln x integrates to 1 over x. That's not true. ln x differentiates to 1 over x. And that's exactly what we're going to exploit when we use parts. You could memorize the result. This is something you'll be expected to do from time to time in A-level maths or in A-level Further Maths, to integrate ln x. But it's not common enough or easy enough to remember that people normally do it. I certainly wouldn't be able to tell you off the top of my head what it was. I'd work it out by parts each time. But every time I do it, I get a little faster, and I'm used to spotting when I need to. The trick is that if we can differentiate ln x, and the trade-off being we integrate the number 1, which is arguably always there as a factor of a trivial product like this, then we'll end up with making 1 more complicated. But although ln x doesn't look much like a linear function or whatever, the derivative is something that does combine nicely with something like x. So we end up with an integral that's just x times 1 over x, which of course is the integral of 1, and the integral of 1 is x. So that tidies up the integral of ln x for us. If we also take into account the minus 1 in my original integral, then I get this, x ln x minus x, and then take away another x for the integral of minus 1. And then I sub in my values, e cubed and e squared, subtract away, everything cancels down, and we're left with pi e cubed, just like the previous bit. So just like the note says in the textbook here, it is sometimes possible to convert your parametric equations into Cartesian form, and if you can do that, you should find the integral works out just the same. In this case, no matter which integral we chose, we ended up needing integration by parts to deal with it. One of them because it was something linear multiplied by an exponential, and in this case it was because we had the natural log, which also requires parts. Sometimes it's going to be easier to do one method than another. It's not a hugely common type of question to get in an exam, but you'll see them from time to time. The last thing I'd recommend, if you get the chance, is to try a couple of questions from the student exam questions. So this one is Corpio 2, Chapter 4, Exam Questions and Mark Schemes, page 13. I quite like this one because it starts out with a chunky 5-marker that is a throwback to complex numbers. Can you prove this general result, which will allow you to work with something like cos to the 6th theta, turning it into multiple angles involving cos theta? Once you've created that formula, or even if you don't manage to successfully create it, it's provided effectively in part A. You can then use it for the later bits of the question. If you can't go and find that particular question at this point, this is the first half of the question. My next slide will give you the second half of the question with all the actual details of what they're asking you to do. Notice so far what they've given you is, oh, this result might be useful, cos to the 6th theta. Pay attention to that. It's going to help with the integral that comes later on. And then here's the paperweight we're creating. Notice some subtle details. It looks like it's not a complete volume of revolution. It's going to be flat on the bottom, a solid paperweight with a flat base, and the curve involves cos cubed. This is the second half of that same question. If you work through this question and you want to check your answers, go to page 13 of the student exam questions and you should be able to check for yourselves.